Greetings viewers, this video will look at Cambridge A-Level Further Maths Syllabus Code 9231 and Further Pure Paper 2. This is variant 4 from the May June 2025 series. We'll attempt question 6 now. The previous questions has been uploaded to the same playlist. So question 6 is giving us a differential equation with some boundary conditions and wanting to give us want us to give the answer in an explicit form y as a function of x. Now, it's not immediately obvious what type of differential equation this is, but if you've done your practice, we can go ahead and divide. You can see if you divide the whole thing by x, and we get this form of differential equation, which if we can recall, is something similar to this form. This one we call as a linear first order differential equation. And to solve this, we're going to need something called the integrating factor. The integrating factor mu of x, it will be e to the power of the integral of px with respect to x. So our px in this case, that will be 1 over x or negative 1 over x. Let's finish the proof of this linear first order solving first. To solve this, the whole equation will multiply by the mu of x. And let's see what happens on the left hand side of the equation. Right, so the left hand side becomes this one, and this is something or we can use the product rule to simplify this into the derivative of mu x multiplied by y, which is the dependent variable. So you can try and prove yourself. If you expand this, given what we already set mu x, the integrating factor, to be e to the power of the integral of px, when you differentiate using the product rule, you should be able to get this expression. So we know that the left hand side reduces to the derivative of mu x multiplied by y, and the right hand side remains as is. So the right hand side we can integrate, and the left hand side we can integrate. Then therefore, let's continue to solve this. Given our value, or given our expression of px, you want to find the integral of px first, right? Integral of px respect to x. So that is negative 1 over x. Integrate, you'll get a negative natural log of x. So our integrating factor, mu of x, will get e raised to the power of negative natural log of x. Of course, this negative, I can raise it to the power of the x using the logarithm rules, right? So the negative in front, I'll raise it to x power negative 1, which gives me just 1 over x, because the natural log and the exponential cancels. So this is my integrating factor, for which I will multiply both sides of my equation with. So going back to this original this original differential equation, I'll multiply both sides throughout with this 1 over x. And so as we already proved, the left hand side, it will reduce just to become the derivative of the integrating factor, which is 1 over x multiplied by y, which is our dependent variable. And on the right hand side, we're just gonna do the algebra like that. And now we can separate the variables. On the left hand side, we have the differential of y over x. On the left hand side, we have 2 tangent inverse x dx. Then we can integrate both sides. On the left hand side, the integral is easy because the integral and the differential cancels each other. But on the right hand side, we have the integral of the inverse tangent of x. There is not, this one does not exist in the formula sheet, right? If you try and find the integral formula, it does not exist there. So what we're going to do is a trick, integration trick. So we're going to use integration by parts. And so for integration by parts, you have this formula, u dv uv minus v du. So this one come from the product rule. And yeah, to choose v or to choose dv is the one that we see is easier to integrate. So we're gonna have to differentiate something, and we're gonna have to integrate something. To differentiate, we're gonna differentiate u, and to integrate, we're gonna integrate dv. So we're gonna assign these two values. For D, I'm going to definitely take the derivative of tangent inverse x, because obviously I don't know how to integrate it. And for dv, I'm going to take 1. So v will just be x. Then for u or du, we differentiate it to become 1 over 1 plus x squared using the formula sheet. So this one, the derivative of inverse tangent is given in the formula sheet, so it's here. Okay, and the next step will be to apply the formula. So u multiplied by v minus v multiplied by du. And so I'm gonna rewrite this integral. So y over x will be equal to 2 multiplied by uv x tangent inverse x minus the integral of x over 1 plus x squared dx. Alright, so we're gonna have to deal with this integral some more. So this integral, what we're going to do is going to use a substitution, because the top looks like something we can be taken as a derivative from the bottom. So we're gonna assign the bottom to be u, or the denominator to be u. So u will be equal to 1 plus x squared, and du will be 2x dx, where we can isolate dx to become du over 2x. And here we're going to just substitute this integral back. So we write everything first. So the denominator, we already assigned it as u, and dx we have taken the derivative to become du over 2x. And so this x and x cancel, and the 1 over 2 you can take it out of the integral because it's a multiple. And we're left with, so this is a fairly simple integral, which is just becoming the natural log of u, right? So I'm going to rewrite everything. So half of natural log of u. And u, I'm just going to straight away substitute back as the original function which we have assigned, which is 1 plus x squared. So that it will be u, and then we've finished the integral, so we add a plus t. So y over x is this one. Alright, up till here, we finished the integration part, but we're still missing this arbitrary constant. So we're going to use these boundary conditions to find it. So we're given that y of 1 will be half pi. So y of 1 equals to pi over 2. So we're going to substitute these values here. Okay, to evaluate this inverse tangent of 1, if you can recall this triangle, if you have this 45, 45, 90 triangle, the opposite of the pi over 4 for 45 degrees is unit length of 1, and also the adjacent is unit length of 1. So the tangent of 45 degrees is 1, and therefore the inverse tangent of 1 will be 45 degrees, or pi over 4 radian. Remember, in calculus applications we use radian. So here we have pi over 4 and 1 over 2 ln 2. So after simplification, you should be able to get c is ln 2. So our final solution, y over x, you can just rewrite the entire thing and even simplify it even more. And they want it in the explicit form y equals as a function of x. So y as a function of x, you just multiply it both sides by x, and yeah, you should be able to get this expression. It's just algebra at this point. And this will be the final answer. Okay. Add x ln 2. And yeah, this is the final answer for this question 6. Thank you for watching.